right? So once we've made epsilon small enough so as to eliminate any of those little bumps, like that. So when epsilon is small enough, very close to 0 on the positive side, then there are no bumps like that anymore. We just have little sections like this. And then the number of terms, capital J, just stays constant as epsilon continues to shrink to 0. So we basically have like a fixed number of terms, and then every term is going to go to 0. Right? So how do we know that every term goes to 0? All right, well, it's clear that the lengths of these intervals are all going to 0. Right? For example, the length of I1 is clearly going to 0. And the same is true for all the I sub j's, in fact, for each j. By the length, I just mean the right endpoint minus the left endpoint. Okay, that's just by continuity. It's because the function phi is continuous everywhere, right, on the entire real line. So you see that as you bring this height level down, let me be a little more precise. It's continuous and also it's monotone. So you see that, for example, this point here is decreasing in height toward the height of that point. And because the red piece of the curve is continuous, unbroken, you see it follows that the horizontal extent of that interval is also shrinking to 0. Okay, so the lengths of all those intervals are all going to 0. And then what about the change in f on those intervals? If those intervals are all shrinking to 0, does that mean that the change in f has to go to 0? Okay, well, it does, but it's a subtle matter, because remember that f can have points of positive mass. Let me just draw a little picture. Like in general, when you have a CDF, if it has a jump discontinuity, let's say it has a jump discontinuity at some point alpha. So that point alpha is like a point of positive mass. In other words, when you go from just before alpha to just after it, no matter how tiny of a jump that is, you're picking up a positive amount of this jump value j of alpha, which is positive. So you pick up a large amount of change, even though you've made only a small amount of horizontal change. So a very tiny horizontal change past alpha will involve picking up a large vertical change, including at least the amount j of alpha, which is strictly positive and can be quite large. Well, okay. Has to obviously be between 0 and 1, but it can be a big chunk of a jump. So because of the presence of that possibility, we have to worry about the change in f kind of including one of those points of positive mass. And therefore, even though the interval I sub j is shrinking to 0 in length, but maybe the change in f is not shrinking all the way to 0. Okay, but I claim that that doesn't happen. And the reason it doesn't happen is as follows. If there's a point of positive mass inside the interval, so let me, so actually first I should emphasize that the points on this line are fixed. Like this endpoint here is just fixed because y is fixed, and it's y plus epsilon that's like decreasing. So like this other point here is going to sort of slide down like that, or you can think of it this way, this endpoint is moving. This endpoint moves back toward the fixed endpoint. That's how these intervals are shrinking. Okay, so if there's a point of positive mass somewhere in here, then that's just going to be surpassed eventually by the moving point. Right? As that moving point moves toward the fixed point, the gray one, that point of positive mass that I've highlighted in green here on the x-axis is just going to be surpassed anyway. Okay, so the only point of positive mass that would actually matter would be like at this fixed endpoint itself. Suppose that that fixed endpoint is itself a point of positive mass. But you see, that's okay because that's already included in the sublevel set of y. That point would have been included in the sublevel set of y, which is being subtracted away, right? That point is included in this set, which is being subtracted away. So actually that point is not contributing its mass at all to the change in f. So because points of positive mass just don't play any role in these delta f's, by the nature of things here, I'll say it one more time, basically because each one of these intervals has a fixed endpoint corresponding to height y, and then a moving endpoint corresponding to height y plus epsilon, where epsilon changes. So as the moving endpoint moves toward the fixed one, any point of positive mass for capital F will be surpassed. That's like in the interior of that interval, as the interval shrinks toward its fixed endpoint. So only a point of positive mass at that fixed endpoint would actually matter, but it doesn't, in fact, because such a point already belongs to this sublevel set. So when you subtract that away from this other sublevel set, you're just getting rid of its mass as well. So that means that these changes in F really do go to 0. Okay, so you see we have to work pretty hard to get a rigorous proof of the right continuity, but we now have it. And that corrects this slight flaw that I said, this proof of right continuity that I gave wasn't entirely rigorous, or wasn't entirely complete. But now we've gone back and completed it. And the nice thing is that it also gives us the proof that when big F happens to be continuous itself, in other words, if there's no jump discontinuities at all, suppose big F just looks like this. Between height 0 and height 1, it just sort of does that. And it could be asymptotic to the height 1, or it could achieve the height 1 and stay there forever. But imagine it looks like that, which is going to be the case when x hat is a continuous random variable. remember that a continuous random variable has a continuous CDF. And actually, it's a little more than that. The CDF also has to be piecewise C1. So continuous random variable really means two things. That capital F is continuous on the entire real line. And then secondly, capital F is piecewise C1. But yeah, we can also now easily prove that the continuity of big F implies the continuity of big G. So that's going to go halfway toward showing that G has these same two properties. Right? G is also continuous everywhere and also piecewise C1. But the fact that G is piecewise C1 is going to have to wait a little while. Right? But you see, that's going to tell us that G has the same two properties as F, which is going to tell us that the new random variable that we're defining here is also continuous in that case. So we get this nice theorem that if x hat is continuous, then phi of x hat is also continuous, as long as phi is a nice function. Okay. Okay, yeah. So part of proving this is showing that if F is continuous everywhere, then so is G. And we can modify this proof that we did here to prove the continuity of G in the case when F is continuous. Okay, the way we modify this proof is just by allowing epsilon now to be either positive or negative. Okay, but to appreciate how that works, I really should be a little bit more explicit about where I used the right continuity of F in this proof, the proof we just laid out here. Where in this argument did I ever use the fact that big F is right continuous? Surely, right, to prove the right continuity of G, we should really be using the right continuity of F. Okay, well, let's take a careful look at it. We're really just trying to prove that the change in F between these 2 points goes to 0, and also similarly between those 2 points. Because those are the two cases that can occur. Either both of the points will be on a red piece, or they'll both be on a green piece. Let me just draw a new picture. Remember that between our two horizontal lines, with one at a fixed height, y, and the other one at a variable height, y plus epsilon, if we have something like this, or if we have something like this, we can ignore those, because as epsilon shrinks to 0, like this line is going to come down, and eventually when it's slowed down enough, you see that you're just going to get 2 points on a green piece, which make a short interval, and then 2 points on a red piece, which also make a short interval. We just need to prove that the changes in F are very small in absolute value. Okay, and remember that the issue there was the presence of points of positive mass, points where F has a jump discontinuity. Okay, so the green pieces actually work very, very simply. If we just go back to the actual formula for G, this is probably the best way to do this, and just look at the actual formula for G, you'll see that because both of these points are on the same green piece, let's call it, phi n or whatever. So what you're going to end up with is f of phi n inverse of y plus epsilon minus f of phi n inverse of y. That's just what comes out of the actual formula for G. Okay? And then in the case of a red piece, if you look at the corresponding formula, that's the other case, where we have a decreasing piece. That difference is going to look like this. It's going to be f upper minus of phi n inverse of the smaller value, and then minus f upper minus of phi n inverse of y plus epsilon. Okay, the reason this happens is because it's this term with its minus sign that appears for the right endpoint. Sorry. Better, let me say it a little better by saying that since phi sub n is decreasing, therefore phi n inverse is also decreasing. And notice that y is less than y plus epsilon, because I was assuming all along that epsilon was positive. So therefore phi n inverse of y is actually greater than phi n inverse of y plus epsilon. So what I'm doing is I'm taking the smaller value right here. That's the smaller of the two. And I'm plugging that into f minus, f upper minus. Then I take the larger of the two values, and I plug that into also f minus, f upper minus, and I take the change. So those are the actual changes. When I write something like delta f, it's just really a shorthand for this in the increasing case, and it's a shorthand for this in the decreasing case. Okay, I usually write like a double up arrow for a strict increasing function, or a double down arrow for a strictly decreasing function. Okay, so anyway, we have two different formulas. Now, let's think about what happens as epsilon goes to 0 from above. Right? If epsilon goes to 0 from above, so of course y plus epsilon will approach y from above. Phi n inverse of y plus epsilon will approach phi n inverse of y, because each phi n inverse is continuous on its domain. Okay, its domain, let me just call it like j sub n. So I'll introduce this notation j sub n for the domain of phi n inverse, or in other words, the range of the original phi sub n. Okay, so that's an interval. Okay, now coming back here, this approach, this last final approach that's being denoted here, is actually approaching from above. That's a very important fact. And the way I know that is because you see y plus epsilon is approaching y from above. And the function phi sub n inverse is increasing. So it preserves the sense of direction. If y plus epsilon is bigger than y, which it is, since epsilon is positive, then phi n inverse of y plus epsilon, phi sub n inverse of the larger value, is bigger than phi sub n inverse of the smaller value, because it happens to be an increasing function in this green case. I probably should draw this in green. This is, remember, the case where phi n inverse is a strictly increasing function. So yeah, so this is like actually approaches from above, which means that f of this value approaches f of this value by the right continuity of f. In other words, this approaches 0, as epsilon shrinks to 0 from above. And notice that I use the right continuity. It's because I know that this value here is approaching this one from above. And when you have an approach from above, capital F behaves correctly. What I mean by that is that capital F of any point plus is equal to capital F of that point. So if I approach alpha from above, then capital F has the correct behavior. That's what right continuity means. So you see that I'm actually using right continuity at that moment to prove that this delta F in this picture here goes to 0. Okay, now what about the other delta F? This one in the case of a decreasing piece. All right, well, in this case, this value here is approaching this one from below, because the function phi sub n inverse is decreasing. So, this one here is smaller, and it's going to be approaching the other one by continuity. Phi sub n inverse is continuous in all cases, for every n. It's always continuous. So the thing is, though, it's approaching from below. Okay, but f upper minus is actually left continuous. And you see that I'm actually taking the change in f upper minus. I really probably should write it that way. I probably should write this. Okay, this delta f was really just meant to be a very informal notation. But more formally, I really should write it this way, because that's really the thing I'm taking the change in between those 2 points. And that does go to 0, because, again, f upper minus is actually left continuous. It's kind of the left continuous version of capital F. Because remember, the prescription is that anytime capital F had a jump discontinuity like this, we just open up that circle and fill in the other one. And we leave every other point alone. So that's what f upper minus looks like. It's clearly left continuous function. And therefore, because this value here is approaching the other one from below, that's the crucial thing, then a left continuous function will cooperate. It will go to, the change will go to 0. Okay. So yeah, both changes go to 0. Both types of changes go to 0. And then the sum of all the changes, which is this upper bound here, will also go to 0. And that's explicitly where the right continuity of f is used. Okay, well now you see that if f is just plain continuous, if I just delete the term right, put that in parentheses, just think that big F is continuous, then coming back to this argument, it really makes no difference whether the direction of approach here is from above or here is from below. This direction of approach could be either way, because big F is just plain continuous. You don't need the right continuity because you have continuity, period. So we don't need to worry about this direction of approach being from above. And that means that we don't have to worry about epsilon being positive. As long as epsilon is going to 0 at all, the whole argument still works. Okay, and same in this case. So you see that that's basically the proof. That if big F is continuous, then so is big G. Okay, that's one part of it. Now the other part is that if big F is piecewise C1, then so is big G. Right? Because that's the other requirement for a continuous random variable, is that its CDF has to be piecewise C1. Right? And that's also true. And again, the best way to see it, I think, is just to look at the original formula for G of Y. So yeah, the range of phi n, which I've always written like that, I've now given it a notation, Jn. It's the range of phi n. So let me just continue to use that notation from now on. So by J sub n, I always mean the range of the nth piece. I'll just make things a little shorter to write down. Okay, so again, we have these two cases. It's like f of phi n inverse of y minus f of cn minus 1. That's the increasing case. F of cn minus f of, or f upper minus. But notice that now f upper minus does not need to be written, because in this context, I'm assuming here, oh, so I probably should have written, and where am I? Yeah, I need to write something like this. If f is continuous on R and also piecewise C1, right, then so is G. But I want to assume both. I'm going to assume that f is continuous everywhere, and I'm going to assume that it's also piecewise C1. Okay, anyway, so under that assumption, then you don't have to write f upper minus anymore, because f upper minus is exactly the same function as f. If big F is continuous everywhere. So we can just delete that. And that makes the decreasing case look like that. Okay. And then we still have the type 2 terms where y is strictly above the range. And so that's the formula. Now what we need to prove is that this function, capital G, has a continuous derivative at all but discretely many points. This derivative exists and is continuous, except for a discrete set of y values. That's what we want. That's our goal. What we need to prove. Okay, and in doing so, I'm just going to state this lemma that I've actually used before, that a finite union of discrete sets is also discrete. It has to be a finite union. You can't take like a countably infinite number of discrete sets and put them together. That doesn't have to give you a discrete set. But if you have a finite union of discrete sets, then that will also be a discrete set. Okay. Let me just give a word or two on this lemma, and then we'll come back to this goal here. So, first of all, the reason I want that lemma is because there are going to be various different reasons why this may fail to exist or may fail to be continuous. And all those different reasons give like exception points. Now, each reason is going to give only a discrete set of exception points, and there's only going to be a finite number of different reasons why either this fails to exist or why it fails to be continuous. There are various reasons why that can happen, but there's only a finite number of possible reasons. And each one only has like a discrete collection of exception points. So then you just take the union of those finitely many discrete sets, and then you'll also get a discrete set. So that will prove the statement. Okay, but how do I know that's true? So the way it works is like this. If I have just two discrete sets at first, just assume I have two discrete sets. So one of the characterizations of discreteness that we talked about is that it has no finite accumulation points. But another characterization, which is equivalent to that, is that between two finite bounds, let's say alpha and beta, there exist only finitely many elements of the set. Right, so in other words, like if I take a discrete set and I intersect it with, let's say the closed interval alpha to beta, this is a finite set always, for all alpha less than beta, or all alpha and beta in the reals with alpha less than beta. Okay, so that's how we can see, like if I have two discrete sets, notice then that if I just take two finite bounds that are totally arbitrary, the set D1 has only a finite number of elements in between there. Let's say all of these belong to D1. And then the set D2 is going to also have only a finite number of elements in that set. And by the way, they can coincide, right? Like some of the elements might belong to both sets. But just a finite number belong to D2. Okay, well that means that D1 union D2 intersected with that closed interval is also finite. Because it's just the union of those two finite sets. It's the union of D1 intersect the closed interval, union with D2 intersect that same closed interval. And both of those sets are finite, and you're taking a union of... this union here is a union of two finite sets. So this is definitely finite. And that's true for any alpha and any beta. So by that characterization of discreteness, by this characterization here of discreteness, tells us that the union is discrete. And then by mathematical induction, if it works for two sets, a union of two sets, it also works for a union of 3 or 4 or any finite number. Because you can always take like the first k of them as one piece, and then take the next one as the second piece. And this is known to be discrete by the induction hypothesis, and then you can add on one more by this theorem, and still have a discrete set. So any finite union of discrete sets is discrete. Okay, well, so when can this formula here fail to be differentiable? So I claim that if y is in the interior of some j sub n, let me call it, well, okay, what should I call it? J sub m. For some m, so notice that's the interior of the interval, not an endpoint. And if y is not in the set of discontinuity points, okay, actually let me just call it big capital D for brevity, where capital D is the set of points x such that f prime of x does not exist, or f prime of x is discontinuous. And recall that this set capital D is discrete. And that's because big F, because x hat is assumed to be continuous. So that big F is, C0, and also piecewise C1. And it's the piecewise C1 in particular that's important. Just means that the set of points where f prime of x either doesn't exist or is discontinuous, like that set of points x where those things happen, is a discrete set. That's exactly what piecewise C1 means by definition. And that discrete set we're just calling D. Okay. Okay, actually, there's a little mistake here. It's not y that can't be in D. Rather, it's like... Okay, yeah, actually, this is a bit of a complicated condition to state. Let me maybe try to say it this way. If all x in D where D is that set, satisfy y is not equal to phi of x. Okay, that's probably best understood with a picture. So remember that I've got this graph with alternating increasing and decreasing pieces. Say it happens to look like that. That's my function phi. And what I'm saying is that if I have a value y, let's pick out a value y. It's a height on the y-axis. And I'm assuming two things about y. First of all, it's in the interior of one of those ranges for some m. So notice that that's true in this picture. This value of y, it's not the best picture. In fact, maybe I should just fix it. Make it the picture a bit clearer. Okay, so what does this mean? If you look, for example, at this green piece, and you look at its range, which goes from here to here on the y-axis, it's clear that y is in the interior of that range. So if that green piece is, let's say, phi 2, this red one being phi 1, so the range of it, which is this interval on the y-axis, that's j2. And you can see that y is not just in j2, it's actually in the interior of j2. It's not one of the endpoints. Here's the value of y right there. So I'm assuming that condition. And then also I need to assume that if I look at all the x's in the set D, where D is that set of points where some kind of bad thing happens, D is the set of points on the x-axis. D is the set of points here on the x-axis, where certain bad things happen. Like let's say this is such a point belonging to D. That means that at that point, one of two things happens. Either f prime at that point, let me call it alpha, just doesn't exist at all, or f prime of alpha exists, but it's discontinuous there. So f prime is discontinuous at that point alpha. One of those two things happens. And there are certain discrete points, like discretely many points, where those things happen. So what I'm assuming here is that when you plug those points, those x values, for all x's in that set, when you plug them into the function phi, you never get this value y. So for example, if I plug alpha into the function, I get this height. It's not the height y. When I plug beta into the function, I get this height. Also not the height y. Right? Let's say that there's another point in that set, gamma. And I plug that into the function. I get this height. Also not the same as y. So all these heights are different from y. And that's true for all the points x in that set, capital D. The heights are different from y. So then, my claim is that for such points, capital G is continuously differentiable at y. Meaning that G prime exists and is continuous. Capital G prime exists and is continuous at y. Now what are the exception points? The big question is, does that leave over like a discrete set of exception points? And the answer is yes, it does. Because what points don't count as y values that meet these conditions? Right? I have these two conditions. This is condition number 1. And then condition number 2 is here. So when we eliminate points that like fail to satisfy those conditions, are we left with almost all points? In other words, the points that don't satisfy those conditions, do they form a discrete set? That's what I'm asking. Okay, and the answer is yes, they do. They form a discrete set. Why? Because the only y values that fail the first condition are the endpoints of all of the jm's. Right? So for example, this point here is an endpoint of one of the jm's. This point here is an endpoint. If we look at some other jm's, like for example, there's also this interval from the piece phi 3, kind of from here to here. And so this point is also an endpoint of one of the jm's, one of those ranges. But there's only a finite number of those. Right? These points here on the y-axis, there's only a finite number of these, because there's only a finite number of jm's in the first place. There's only a finite number of pieces. Phi 1, phi 2, phi 3. In this case, there's also phi 4. But always, you only have a finite number of pieces of your function. And so the number of ranges is also finite, and then the endpoints, like the set of endpoints of those ranges, is also finite. So there's only a finite number of points y that fail condition number 1. Okay, what about condition number 2? Well, the set D is discrete. So there's only a discrete set, alpha, beta, gamma, like those points. And there may be many of these, there may be infinitely many, but it's a discrete set. And my claim is that when you plug those into the function phi, you just get a discrete set of values on the y-axis. Okay, let's think about that. For example, when you plug alpha into the function, you just get exactly one height. There's whatever that height is, it's this height here. Okay, then when you plug beta in, you're going to get some other height. Those two heights are distinct, because alpha and beta are distinct, and they both happen to be like on the same green piece. Okay, now it might happen that the same height, like where, let's say, the height at alpha might also be the height at some other point, like here. Let's say this is delta, also in the same set, capital D. So that could happen, but that's actually in our favor when that happens, because it means that the number of points on the number of distinct points on the y-axis is possibly even smaller than the number of distinct points on the x-axis. See here we have two distinct points on the x-axis, alpha and delta, that both map to the same point on the y-axis. So the number of points when we go to the y-axis, we look at the corresponding points on the y-axis, is even fewer, possibly. but it certainly can't be greater. Okay, but how do I know that those points on the y-axis, corresponding to these alpha, beta, gamma, delta, won't accumulate toward any finite point? So the answer is that for a finite interval, like if I'm looking only in, let's say, for a green piece, in that finite interval from, let's say, Cn minus 1 to Cn, there can only be a finite number of those special points, because it's a discrete set. So let's say I have a finite number of those points, let's say they're alpha, beta, and gamma. And then you just have a finite number of heights on the y-axis. And that's going to apply to each piece. Each bounded piece, that is. So for example, the very next piece will go from Cn to Cn plus 1. Let's say that's a red piece. They join here. And again, between those two bounds, there's only going to be a finite number of those special points, the capital D. Let me call them, I don't know, kappa, sigma, rho. All of these are like elements of capital D. Okay, so then, again, there's only a finite number of corresponding points here on the y-axis. So basically you see that between any two finite bounds on the y-axis, there's only a finite number of these. And that's because there's only a finite number of pieces. And each piece, by piece I just mean like a green, one of these green sections or one of these red sections. There's only a finite number of those pieces overall. And each piece is contributing only a finite number of points on the y-axis. So these special points on the y-axis, which are the bad points. So between any two finite bounds on the y-axis, you're only going to have a finite number of those. And that means you're getting a discrete set. Okay. Now, there is one problem, to be absolutely honest with you, which is that the very last piece, let's say, or the very first one, goes on forever, like all the way to plus infinity. And there may be a countably infinite collection of points in D, like in there. And they don't accumulate, of course, they just go all the way to plus infinity. But let's say that happens. Let's say I have all of these points that are also in D. Oops. And they're going off to plus infinity. Now they also give like corresponding heights on the y-axis. So what can I say about those heights? Well, there's no problem if it's unbounded. See, if this piece is unbounded, if it's going off to plus infinity, or maybe if it's a red piece, if it's going to minus infinity, then there's no problem, because these are going off to plus infinity, these black points on the x-axis, and then because the function itself is unbounded, the images of those on the y-axis. Let me do that, let's say in blue, right? So that's like the image of that first point, then I have the image of that second black point, third one. Well, those are going to be going to plus infinity, just by the fact that the function itself is going to plus infinity. As you move right indefinitely far, the function moves, indefinitely upwards. So if the last piece is unbounded, there's no problem. Those blue points on the y-axis will not accumulate toward anything. They'll just go off to plus infinity. They have no finite accumulation point. And actually, it's actually a very subtle question, because what if the green piece was increasing forever, but what if it like went flat temporarily, just for an instant, on its way to plus infinity? If it achieves, horizontal tangent line for a second, then you can have something bad happen, because then, well, no, is that what I want to say? No, I guess that's okay. No, but the only thing that's not okay is if there's a horizontal asymptote. Let me show you what that picture is going to look like. So let's say I have like this red piece, and then I have a last one, which is a green piece, but it's approaching a horizontal asymptote. Okay, so then if I have a bunch of points on the x-axis which are in the set D, and they're going off to plus infinity, and you look at the corresponding heights on the y-axis, they are accumulating toward a finite value. Namely, they're accumulating toward the height of that horizontal asymptote. So you see, in that case, the set of points wouldn't really be discrete. So this could present a problem. Now, the truth of the matter is that the restriction to like discretely many bad points is really quite artificial, and it's not really necessary. I think I may have mentioned in a prior video, a very early video in this whole probability series, I think I did mention that actually there's really no problem with a countable number of bad points, a countable set of bad points. The problem with it, from our point of view, is that it's a lot harder to prove theorems. When like the set of exception points, okay, by exception points I mean like points where one of these two things happens. F prime either doesn't exist or fails to be continuous. If you have a countable collection of exception points, not necessarily discrete, so it can be very like densely distributed, like the rationals, you can still make the theory work. It's just a lot harder. The proofs of the theorems are a lot harder, and you don't do it the way we're doing it right now. You have no chance at using basic calculus. You have to use very fancy stuff like measure theory and abstract integration theory, Lebesgue integration theory. So we really have no chance at building an elementary theory, something that is presentable at the level of a high school class. Even now, we're having to work extremely hard, even with like this very artificial restriction to a discrete set of bad points. So the fact that these points aren't quite discrete, in the case when you have a horizontal asymptote, as your last piece has a horizontal asymptote, or maybe could be your first piece, right, on the left side, could also have a horizontal asymptote. Let's say something like this. But anyway, those cases violate this property that the exception points have to be discrete, or they can anyway. See, it doesn't have to violate it, because the set D may not contain these points. It just can. There's the possibility that D has these points going off to plus infinity. And therefore there's the possibility that these corresponding points on the y-axis accumulate towards something. It doesn't have to happen, but it can happen. And that's, a problem for a general theorem. Something bad can happen, then a general theory can't, right? We can't prove a general theorem. A general theorem has to work without exceptions. Okay, so, like I said, this constraint of making sure that the exception points form a discrete set is not really necessary to build a successful theory. We can actually allow a countable set. And then it's very clear that the image points on the y-axis work perfectly fine, because the bad points on the x-axis are countable, and then their images under the function phi are also obviously countable. Each x has a unique y, because it's a function. This function phi is a function, so it maps each point x on the x-axis to a unique y value. So, you have a countable set of x's, and then you'll have a countable set of corresponding y's. So if countability is your criterion for the exceptional points, then there's no problem. Okay, but just to keep things rigorous within the context that we're working in, where it's discreteness that matters, I'm going to now modify the class of nice functions to exclude this case. In this case, I'll just say that a nice function has to be unbounded at both ends. Okay, so that will include, for example, all polynomials. Every polynomial is unbounded at both ends. Polynomial, like, a cubic polynomial looks like that. So you see that it has like this increasing piece that's unbounded on the left, followed by a decreasing piece, followed by an increasing piece that's unbounded as you move to the right. Okay, so like a cubic polynomial or any polynomial would be a perfectly fine example of a nice function. It doesn't have to be a polynomial. For example, like you can have cusps. You can just create something very artificial if you like. You can take something like this and just make a cusp, make another cusp, because the presence of a finite number of cusps is okay. It doesn't hurt anything. But I'm now saying that like the last two pieces have to be unbounded. For example, they could both go to minus infinity. And this is specifically to avoid this problem here of the set D having corresponding points on the y-axis which accumulate toward any finite value. And why do I want that? Because I want to prove that this condition 2 here is also a discrete condition, meaning that like the set of points that fail that condition is a discrete set. So the set of points that fail condition 1 are just the endpoints of the J sub m's, and those are discrete because they're finite, in fact. There's only a finite number of them. And then also the set of points that fail condition 2 are also a discrete set. Okay, and then the union of those two is also a discrete set, because again, the union of a finite number of discrete sets is discrete. Okay, so now I'm going to try to prove this claim. Where did I make the claim here? Yeah, here. That for all points other than those, for all points y other than the endpoints of the J sub m's, and other than the images of these exceptional points on the x-axis, any other y value at all is such that capital G has a continuous derivative at such points. G prime, capital G prime exists and is also continuous at such points. Okay, and it really just comes directly from this formula. If you stare at the formula, but there's a little bit of a subtlety to it, because notice that the y appears in the summation sign as well. In a derivative, you have to let y change a little bit, because the derivative is just the limit of the difference quotient. So I have to look at this difference quotient and then prove that it has a limit as h goes to 0, at least for most values of y. The point is to prove that for most values of y, meaning all but discretely many, all values of y except for a discrete set, this limit will exist. And not only will it exist, but it will represent a continuous function of y as well. Anyway, so because we have to let y vary a little bit, we have to go from y to y plus h, we have to be concerned with the presence of y in this condition. Okay, so we need a little bit of room around y, right, to be able to move up by h or down by h. So actually this shows me that, I think I made a slight mistake earlier over here, where, yeah, okay. So what I really want to say here is for all m. So I may as well just call it n. Not some, but all. So in other words, the y values that we want are the ones that are in the interiors of all of those ranges. In other words, they're not endpoints of any of them. The endpoints of those ranges are going to be excluded, but again, there's only a finite number of those. So the ones that are left are the ones that are not endpoints of any of them. And that means that they're interior. So of course it can't be interior to all of them, but rather to interior or just not in at all. Right, for all n. So let me just illustrate that in the picture. For example, look at this y value here that I've picked out. It's the height of this blue horizontal line. Right, you see that, okay, that value of y happens to be in all of the ranges in this picture. It didn't have to be that way. I can still make it so that it's not, just by adding another piece. Like, let me add another decreasing piece here, and then another increasing piece, let's say, over here. Okay? So if you look at this little range, the range of this red piece, that would be some interval over here, let's say, on the y-axis, that doesn't contain y at all. But for those ranges that y is in, it's not an endpoint, but it's rather an interior point. So either y is in the interior, or y is just not in it at all, for every single n. or we can say it like y is exterior. That's probably a better way to think of it. Either y is interior or y is exterior to every one of those jn's. So it's not an endpoint of any of them. And remember that because the set of such endpoints is finite, basically there's only a finite number of j sub n's, and each one has just 2 endpoints. So you have a finite number of those endpoints. All other points y will satisfy this condition, condition number 1. They'll either be interior to every jn or exterior to every jn. I said that wrong again. For any n, y will be either an interior point or an exterior point. Because the only way that fails is if y is one of the endpoints. And we know that we've deleted all such points, but there's only a finite number of those anyway. So certainly discretely many. Okay, yeah, so with that correction, let's come back here. And now you see that we do have a little bit of room around each y that we're considering. Because we're only considering those values of y that satisfy conditions 1 and 2. The claim that I'm making here is that when y satisfies both conditions 1 and 2, meaning it's not any of those endpoints, and it's not the image of any of these points in capital D. It's not like the phi value of alpha or beta or gamma or delta. So yeah, for such points, I want to prove something about the derivative of capital G. But you see, for such points, I have the room I need, right? Because, let me just draw you a little illustration here on the y-axis. If I have such a value of y, it's going to be, let's say, interior to one of those ranges, and then maybe it's exterior to some other range. But either way, a very tiny movement of y, either up or down by a very small h, will keep it within the interior of the red interval, and also keep it within the exterior of the green interval. And there may be many of these, but only a finite number. It's like, let's say here's another one of those ranges, and let's say here's another one of those ranges. So y is interior to some of them. Maybe another range looks something like this, right? Y is interior to some of them. For example, y is interior to this one, and also this one, and also this one. But this one, y is exterior to that, and this one also. But if you move y very slightly, up or down, it stays either in the interior of one that it was already in the interior of, or it stays in the exterior of one that it was in the exterior of. Okay, so the condition that y belongs to Jn is stable under a small movement of y. This condition stays true, or is stable, under a small perturbation in the value of y, either up or down, it doesn't matter. And then the same is true of this condition here, also stable under a small perturbation in y, because whether you move y up or down, if y is strictly greater than one of those ranges, like let's say y is like strictly greater than this range, Jn, a small enough movement up or down is going to keep it greater. Whether you move it up or down, if it's a small enough movement, it's going to stay strictly greater than that range. So it's going to stay true. And therefore, the set of n values for which this condition is true does not change as you move y up or down by a sufficiently small amount. And also the set of these n values. Those are two different sets, by the way, because the two conditions are contradictory. This condition here and this condition here are mutually exclusive conditions. So the set of n values that satisfy that one is disjoint from the set of n values that satisfy that condition. But both sets are stable. Both sets do not change when you move the y value by a small enough h. Okay? So then the number of terms does not change. And the subscripts n that are involved in those terms do not change. Like the set of n values, the set of values of that subscript n in this summation does not change. And the set of n values involved in this summation also does not change. Okay, well, that tells us something. See, this is just a constant. It depends on n, of course. It's a constant depending on n. But since the set of n values is unchanging, that whole sum is unchanging as you move the y. I guess what I mean to say is that this quantity here does not depend on y at all. It has no dependency on y. So because the set of n values that satisfy this condition is stable when you move y a little bit, those terms are actually perfectly constant. The number of such terms stays, like all those terms just stay exactly fixed as you move y. And you don't gain any new terms or lose any terms because the set of n values stays stable. Okay, what about these terms? Here, the set of n values stays stable, but the terms themselves are functions of y. Right? Like you see that y appears here, or in this type of term, y appears here. So as a function of y, the question is it a differentiable function? Now, we don't have to worry about this term because it's just a constant, and we don't have to worry about this term because it's just a constant. Like adding or subtracting a constant doesn't affect differentiability. So all we have to worry about is this composition, f composed with phi n inverse, or this composition, f composed with phi n inverse. The question is that a differentiable composition? And the chain rule tells us when that will be differentiable. It will be differentiable at any point where big F is differentiable, and where, so okay, I have to say it a little carefully. It's going to be differentiable at any y value for which phi n inverse is differentiable at that y, and such that big F is differentiable at this point, phi sub n inverse of y. Like that's the point getting plugged into big F. So big F has to be differentiable there. Okay, but if you think about it, the conditions on y that we are assuming, which are conditions 1 and 2 here in this claim, conditions 1 and 2, exactly tell us that the y values we're looking at are not the images of any of these bad points x that belong to D. So that means that we don't have any issues about f prime not existing or being discontinuous, because the only places where we have those issues are at these points of capital D. But the y values we're considering are not the images of any of those bad points. So therefore there's no issue with big F being differentiable. Big F will indeed be differentiable for the y values that we're considering. In other words, what I'm saying is big F is indeed differentiable at phi n inverse of y, because phi n inverse of y is an x value that is not in D by condition 2. Okay, remember that. So let me just have a new slide here. I'll do it down here. You see, if phi n inverse, let me just call it x, if that were in D, then you could take phi n of both sides. And then phi n just coincides with phi, because it's a restriction of phi. And you see this x would belong to D. So that means y would be expressible in the form phi of x for some point x in the set D. And that's a contradiction. We're explicitly assuming in assumption 2 here that that is not possible. You cannot express y as phi of x for any point x in D. So you see that there's no problem with f. F will be differentiable at the points we're considering. The only question is, will phi sub n inverse of y be differentiable? Like, will this inner function here actually be differentiable? And the answer is yes, because remember that all of those pieces are differentiable in the interiors. Like at endpoints, there's no guarantee. You'll remember I pointed out that even for a very simple function, such as x squared, if you look at this green piece, because its tangent line goes horizontal at the origin, when you go to the inverse function, so like this would be phi 2 of this function. Phi 1 is this decreasing piece. Okay, but anyway, when you look at phi 2 inverse looks like this. It's an increasing function strictly, but it's not differentiable here at the origin. So at one of the endpoints of its range, of its domain, which is the range of phi 2. So that also becomes the domain of phi 2 inverse. But at one of the endpoints, namely 0, it's not differentiable because the slope is like infinite. But at least in the interior of J2 or whatever, J sub n, it will be differentiable. It will have a unique tangent line. And that's because of the inverse function theorem. The original function, the original phi sub n, has a derivative of constant sign, strictly positive, let's say, throughout the interior of its domain. And because it's of constant sign, never 0, the inverse function theorem tells us that the inverse function is also a differentiable function. So yes, as long as we're in the interior. Now, are we in the interior? Well, we are because of assumption number 1 in our claim, right? Because of this assumption number 1, y is not an endpoint. That's really what assumption number 1 is saying. Y is not an endpoint of any j sub n, at all. So it's never an endpoint of any of the j sub n's, and therefore it's never a point where phi sub n inverse fails to be differentiable. If phi sub n inverse is applicable to that y at all, then it will be differentiable at that value of y. So you see, the inner function is differentiable at that value of y, and then the outer function is also differentiable at phi sub n inverse of y, by what we said here. So therefore, the chain rule tells us that the composition of the two is also differentiable. Okay, and the same argument, of course, works if the term looks like this, if it's the decreasing case rather than the increasing case. So you see that the set of n values stays stable as we move the y. So this summation doesn't change, like which terms are involved, which n values are involved doesn't change. And then the individual terms in that sum also will represent differentiable functions of y. Okay, so where are we now? We've just proven this claim that g prime of y exists, at least except on a discrete set. And what is that discrete set? Well, it's the set of points that fails either condition 1 or condition 2. The points that fail condition 1 are discrete. The points that fail condition 2 are discrete. And then the union of those two sets is also discrete. That's the set of sort of bad points where capital G prime of y may not exist. But it's just a discrete set, so we don't care about it. Okay. But what about the continuity of G prime? That still remains to be discussed. But fortunately, that's very easy, because the exact same argument applies. We just have to look and ask, when you do the derivative, will the result be continuous? And the answer is yes, because big F is not just differentiable at this point, but in fact continuously differentiable. That's part of the definition of a continuous random variable. Big F is piecewise C1. So yeah, when you're away from the bad points, right? When you're away from that set capital D, then big F is not just differentiable, but actually continuously differentiable. So big F prime is going to be a continuous function. And also, phi sub n inverse is not just differentiable in the interior of its domain. It's actually continuously differentiable. Let me come back to this picture here. Yeah, here, like the slope of this tangent line as a function of this point y is continuous. As y moves, the slope changes continuously. So in other words, phi 2 inverse prime doesn't just exist, but is actually continuous. So yeah, it exists and is continuous. for all y in the interior of J sub 2, or more generally with any index, any subscript, as long as you're in the interior. Okay, that's all part of the inverse function theorem. If you're in multi with me, you have seen this. Remember that the inverse function theorem basically says that, it's related to the implicit function theorem. So you start out by assuming you have a C1 function, and then you get a C1 local inverse. And it actually turns out to be a global inverse because the function is 1-to-1 globally. So, the function phi2, for instance, is globally 1-to-1 because it's strictly increasing. And so it has a global inverse function, phi2 inverse. And locally, patch by patch, we have local inverses everywhere that we can piece together to form a global inverse. But each local inverse is in fact C1 by the inverse function theorem. Each local inverse that we patch together to create this global inverse is going to be a C1 function. Okay, now C1 is a pointwise distinction. Like you're C1 at a point. So if you can patch that function together from C1 pieces, overlapping C1 pieces, then the whole thing is a C1 function, at least in the interior. So you see that, in fact, this formula here shows that at the points we're considering, at the points y where conditions 1 and 2 hold, not only is capital G differentiable, not only does the derivative exist, but in fact that derivative is actually continuous too. Because it all boils down to f prime being continuous, and also phi sub n inverse prime being continuous. And that's because the chain rule tells us that the way you differentiate with respect to y, a term like this, the way you differentiate that is just you do the outer derivative with the inner function plugged in, and then you multiply by the derivative of the inner function. Okay, now we just got through showing that this is continuous at y. Why is that? Because f prime is continuous at this point, x. F prime is continuous at x, and then also phi n inverse is continuous at y, since y is an interior point. And then the composition of the two, if you compose them. The composition of two continuous functions is continuous as well. Okay, and then this is also continuous at y. And then the product of two continuous functions of y is also continuous as a function of y. So yes, the derivative not only exists, but is actually continuous as a function of y. All right, and you see that the constant term that you subtract away here doesn't change any of that. This constant term here wouldn't change any of that. Okay, and the summation signs also don't change any of that, because the summation signs, as we said, are stable under small movements in y. All right, so that's a complete proof that... where was the theorem? I wrote it somewhere. Yeah, that's a complete proof of this theorem here. If x hat, the original x hat, is a continuous random variable, then so is phi of x hat, where phi is like a nice function. Okay? Now, remember, I had to modify my definition of nice to basically exclude horizontal asymptotes and require it to be unbounded at both ends. But you can relax that. You can allow the function phi to have horizontal asymptotes. Let me just draw you like a typical picture. Let's say I have a function that looks like this. And let's say I have a horizontal asymptote, which happens to be the x-axis. You can allow that. That's going to be fine if the big F is actually like not just piecewise C1, but actually C1 everywhere. If it's C1 on the entire real line, meaning there's no exception points, because that's going to mean that the set capital D, where bad things happen, is empty. Right? And if D is empty, then the image of D under phi is also empty. And that certainly counts as a discrete set. The empty set is just a simple example of a discrete set. So it works perfectly fine, even if you have a horizontal asymptote. Okay? It's only when big F has bad points that we have to worry. When big F has bad points where it either fails to be differentiable or where its derivative is discontinuous, then you have to eliminate the case of horizontal asymptotes and work only with functions that are unbounded at both ends, such as polynomials. Okay, but you see, most continuous random variables that occur in practice are just C1. The capital F will just be C1 everywhere, like the normal distribution, the Gaussian distribution. That CDF looks something like this. Remember that the Gaussian density is a bell curve like that. And then if you look at the corresponding CDF, which is where you integrate, it's like the area under the curve up to x. So if you plot that, it's just going to be a nice smooth, it's perfectly C1. In fact, it's even C infinity. And that's like very typical in practice. So yeah, in practice, the function phi could have horizontal asymptotes. There's usually no problem with that. It's only when the function f has bad points, discretely many, that we have to make this modification where we don't allow the horizontal asymptotes. And even then, it's only for really kind of artificial reasons. Okay, good. So now we're in a position to start deriving the main formula, which is the formula for the expected value of phi of x hat in the case when x hat is continuous. Okay, and all the work we've done up to now, I know it's been a lot, but all the work we've done in this video up to now really has prepared us to do this calculation. and prove this. It's quite a difficult theorem to prove, but yeah, the work we've done so far will really help us. Okay, so here's how it's going to help us. What I'm going to say is the following. Let me just remind you of this notion of Riemann equivalence that I introduced. I think I wrote it this way, like with a congruence, like a congruence sign. But for us, in our course, this means Riemann equivalence. And it just means that we write it between two functions that differ. So they're both functions from the reals to the reals, let's say. Actually, they can be complex valued, that's fine. But they differ on a set that's discrete. So yeah, f of x equals g of x for all x in the reals except d, where d is some discrete set. And on that set, they can differ. Okay, so in other words, for x values in D, f of x naught could be different from g of x naught. It doesn't have to be, but it could be. All right, but as long as that set is discrete, then we say that the two functions are Riemann equivalent. And the main theorem about Riemann equivalence is that integrals are always the same. If I integrate f between a and b and I integrate g, then the integrals can't detect any differences. And this is true also for improper integrals, as long as they converge. If one of them, like let's say b is infinite, then the theorem will say that if this converges, then it follows as a conclusion that this one converges too, and they're equal. Conversely, if this one is known to converge, then the conclusion will be that the other one converges, and again, they're equal. So it's not just true for finite limits of integration, it's also true in some sense, you just have to state it carefully, for infinite limits of integration. But, roughly speaking, let's just say it this way, for all a and b in the extended reals. The extended reals including plus and minus infinity, as long as a is less than b, less than or equal. So that's a true fact about Riemann equivalent functions. If they're Riemann equivalent, then we can make this conclusion. Okay, anyway, so let's recall that the density... So, okay, let me introduce a little notation here. We have x hat. It's a continuous random variable. And therefore it has a density. And let's call its density little f. That's the typical notation we use. But let's recall that f of x was defined in a certain way. It's defined as big F prime when x is not in that discrete set D. When x is not a problematic point. Not. But what about when x is a problematic point? Well, then we just define the density as 0. Basically just arbitrarily. Just to give it some value. And remember that D is discrete. And it represents points where big F prime either does not exist or is discontinuous. Okay, so that's the way we define the density, and then the theorem was that you can reconstruct the CDF by integrating the density from minus infinity up to x. Okay. We also have the theorem that, so that's one theorem. We also have this other theorem that if the integral of x f of x dx converges, then x hat is expectable, and its expected value is the value of that integral. Okay, so we proved that in the last video. Good. Now we also have this new random variable phi of x hat, which we can also call y hat for short if we like. But we know that it's also continuous because its CDF is the big G that we studied, and we know that big G has the correct properties, as long as big F does. Right? We just got through proving a little while ago that capital G is both C0 everywhere, continuous everywhere, and also piecewise C1. Provided big F has those same two properties, which it does, by assumption. Okay, so we have a second continuous random variable. Now that means it also has a density. And let's call its density little g, just to distinguish it from little f. Now remember what that's going to be, and I'm going to write it as with a variable y instead of a variable x. So I'm writing the original density with a variable x, and this new density with a variable y. So what that's going to be by definition is capital G prime of y, when y is like outside of some discrete set, we call it capital delta, and then 0 when y is in that discrete set. This capital delta is some discrete set which we discussed. It's the set of points that fail to satisfy one of those two conditions that I labeled conditions 1 and 2. But we know it's discrete. Okay, now the important thing is just that the function g is Riemann equivalent to the function big G prime. Right, now here, so I'm slightly abusing notation because the domain of big G is all reals, but the domain of this one may not be all reals. The domain of this one is just all reals minus that discrete set. But actually, we can build that in. So I should have defined Riemann equivalence a little more carefully. The domain doesn't have to be all reals. The domain can just be all reals minus a discrete set. And then we can just say that they disagree because one of them doesn't exist. You see, that there are basically three reasons they could disagree at a point. One is that they're both defined at x naught, but they just have different values there. Another is that f exists at x naught, has a value, but g does not. So they can't be equal. And then the third is that g has a value at x naught, but f does not, so they can't be equal. Okay, so yeah, the domains don't have to be the same even. One of them will have the reals minus a discrete set as its domain, and the other one will have the reals minus a second discrete set, and be complex valued also. And here d1 and d2 are both discrete. So the domains don't even have to be all reals. But you see that there's some discrete set on which they disagree. Namely, you have to take all these points and include them, because f is not defined at those points. And g may or may not be defined at those points. Okay? You also have to include all of these, because g is not defined at those points, and f may or may not be. But then there also may be points in both domains where the two functions just simply don't agree. Right? There may be like perfectly fine points that are in both domains simultaneously, but the functions don't give the same value. So, but anyway, the whole thing is just some big discrete set of where the functions disagree. Okay. Anyway, so with that correction, it's a perfectly correct statement to say that these two are Riemann equivalent. Okay? And it's only Riemann equivalence that we care about for densities. We only have to identify the density up to a discrete set. If we don't identify the density like on a discrete set of points, it doesn't make any difference. It's not going to affect any formula involving integrating that density. Okay, so that's something we want. Okay, and then we also know another function that is also Riemann equivalent to g prime. Namely, it goes something like this. It's going to be the sum over all values of n where y belongs to j sub n. I'll just remind you here that j sub n is just short for the range of the nth piece, phi sub n. Okay, and then you're going to have, let's see, how would it go? We have to differentiate. So f prime of phi n inverse of y times yn inverse prime of y. And then there would have been minus a constant term, but that differentiates to 0. So that's going to be like in the increasing case. And in the decreasing case, remember that there would have been a constant minus big F of something, and we have to differentiate all of that. But the constant is going to differentiate to 0, and there's still going to be a minus. And then you'll have f prime of phi n inverse of y, and then phi n inverse prime of y. That's the formula in the decreasing case. And that's it, because the other terms are the type 2 terms, and those are constant. Those are like locally constant. Okay, let me go back a few slides and just remind you that these terms here, these type 2 terms, are locally constant. If you move the y a very tiny bit up or down, those terms stay stable. The values of n that are included in that summation sign stay stable, and the terms themselves are constant with respect to y. They don't change. So therefore, any function that's locally constant in a particular interval is going to have a derivative of 0 in that interval. So the derivative of those terms at y is going to be 0 for the y values that we're considering. And therefore those terms don't have to be included at all. Okay. So those type 2 terms, when you differentiate with respect to y, they just go away. All right? And so that's what g prime looks like. Let me in fact include the variable y when I write these Riemann equivalences. I'll just include the value of y. Right, so this one we know. That's no problem, because the two functions only differ because little g kind of jumps to 0 suddenly, but only on a discrete set. So they only differ on a discrete set. In every other case, they agree with each other. So yeah, this Riemann equivalence is known. Now, okay, why is this only a Riemann equivalence and not an exact equation? Well, the reason is because, you see, big G prime of y may exist in other cases. It may exist for certain points y outside of that discrete set. Sorry, in that discrete set. When we identified that discrete set, we identified it as the union of all the points that fail condition 1, and then all the points that fail condition 2. But that we cast a very wide net there. We just did that to be safe, to be on the safe side. We knew that all points that satisfied both of those conditions were going to be okay. We're going to give the behavior we wanted. But there may be some points that fail those conditions that are also okay. So in other words, g prime of y might exist or might be continuous even at certain points in capital delta. We just don't know. And yet this expression here, this summation expression, is only going to make sense for the points that we identified. Okay, but again, the two differ by only a discrete number of points. So we can't say that they're exactly equal, since this one here might exist for certain y values that this summation doesn't make sense for. But again, if they exist for differing sets of points, then the two sets will differ only in discretely many points. So it's a correct Riemann equivalence. Okay. And then one more Riemann equivalence would be to replace this capital F prime with little f in both cases. Because remember that those two are Riemann equivalent as well. Right? By the definition, these two agree, except on discrete set. So little f is also Riemann equivalent to big F prime. Okay. And we're just doing that in every term. And there's only a finite number of terms. So it should be clear that if I have a pair of functions that are Riemann equivalent, and then a second pair that are also Riemann equivalent, and you can have a finite number of these, let's say k of them, the sum of all of these is going to be Riemann equivalent to the sum of all of these, as long as it's a finite sum. That's a correct theorem about Riemann equivalence. And the reason is because f1 and g1 agree except on some discrete set, which you can call d1. f2 and g2 will agree except on some discrete set d2, and so on. And then these two will agree on some everywhere except on dk, where dk is discrete. Well, then what about the sum? This sum will then agree with this sum except on, right, you'll get agreement except on the union. But we know that the union of finitely many discrete sets is also discrete. So it's a correct conclusion to say that these two are Riemann equivalent. So you see that the fact that it's a finite sum is very important here. It's a finite sum of terms, and in each term I'm going to replace big F prime with this Riemann equivalent function little f, and big F prime with this Riemann equivalent function little f. Okay? Now the thing is, though, we have to be a little bit careful because there's other stuff in these terms. There's other expressions. Like there's something being plugged in to big F prime, which would also be plugged into little f in both of these places. And then there's also this other thing that's being multiplied. So do those affect the Riemann equivalences? Okay, well, because it's the same factor that's being multiplied in, whether it be big F prime over here or little f, obviously the extra factor agrees with itself everywhere. The extra factor, which is this factor here, phi sub n inverse of y, or sorry, phi sub n inverse prime of y, that agrees with itself. So it doesn't introduce any more like points where the expressions disagree. So that's okay. Having that factor there is perfectly okay, as long as it's the exact same factor in both cases, which it will be. Okay, but what about the thing plugged in? Does that affect the Riemann equivalence? Okay. Well, as long as it's the exact same factor plugged in, then it always agrees with itself at every value of y. And we already know that like a discrete set of x values on the x-axis will correspond to a discrete set of y values on the y-axis by the nature of the way these functions, these nice functions phi, are constructed. Remember, that was the reason why we got rid of the horizontal asymptotes, at least when we had to. Right? When there are bad points around, when big F has bad points, we had to sort of get rid of the horizontal asymptotes from the function phi. We couldn't allow them. And the very reason for that was just to make sure that a discrete set of points on the x-axis, when you plug them into the function phi, you get a discrete set on the y-axis too. So that's going to tell you that the fact that we're plugging in something into big F prime or little f doesn't matter, because there's only a discrete set of values where those two functions differ, and those are values on the x-axis. But there's only a discrete number of y values where phi sub n inverse of y gives you back one of those x values that are bad, where the two disagree. So again, there's only a discrete number of y values where the two expressions will disagree. Okay? So, okay, in a nutshell, what I'm saying is like this. We know that these are Riemann equivalent, right? If I then plug in the same function to both sides, now I have two functions of y, these are functions of x, and they're Riemann equivalent. But I'm now saying that these are Riemann equivalent functions of y. How do I know that? Well, I know that because this tells me that I have this equation for all but discretely many x. Okay? And since there's only discretely many y, for which phi of x equals y for some bad value of x. By a bad value of x, I mean one of these discretely many x's here. By the way, this is by the nature of nice functions. By the very nature of nice functions, phi, we constructed them specifically to have this property that a discrete set of points on the x-axis will always map to, under this function, a discrete set of points on the y-axis. Okay? So therefore, there's only discretely many y for which these two don't agree. And that's what Riemann equivalence means. So those two are indeed Riemann equivalent functions, and then you can multiply both sides. And once you have that plugged in, you can then multiply both sides by the same function, and you'll still get Riemann equivalent functions like that. Okay? And then you only have a finite number of terms in which that is happening, but because of this theorem here, where you can add up, column by column, a finite number of Riemann equivalences, this is okay. So you see, in the end, what we're getting is that the density of the random variable we're looking for is Riemann equivalent to, and that's all we really care about, just determining it up to a discrete set, where we don't know its value. Okay? Yeah, it's Riemann equivalent to the following sum. You take all n values where y belongs to j sub n, the range of the nth piece, phi sub n, and you'll put here little f instead of big F prime of phi n inverse of y, and then the absolute value of phi n inverse prime of y. See, that takes care of both cases all at once. So this is really the formula we want. It gives the density. It gives the density of this new random variable, which we call phi of x hat. At least up to a discrete set, which is all we really care about, because its values on a discrete set can be just set to 0 if we like. We can always change the density as long as we change it only at discretely many points. It really makes no difference. Remember, the density is not unique. You can always jigger with the density a little bit, change its value, as long as you do it only at discretely many points. So, at the points where we don't know the value of g, we can just declare it to be 0, and it really makes no difference at all. Okay, so that determines the density of this new random variable, which is very nice, because we can then use that to calculate the expected value. You see, to try to compute the expected value, we need the density, because we're going to try to use this formula, y times g of y, dy. We know that that formula is true, provided the integral converges. Provided this doubly improper integral converges, because that's part of the last video, Remember, as long as this integral converges right here, it implies what? It implies two things. First, that the random variable in question is expectable, does have an expected value, and secondly, that its expected value is given by that very same integral. Okay, so yeah, provided the integral converges, we're going to get everything we want. So that's the reason why g of y is important to know, at least up to a discrete set, so that we can look at this formula here. Okay, well anyway, how did I get this absolute value here? Where did that come from? That just folds together the two cases. So if you look at the two cases, which I've always been denoting with these curly brackets, there's like the increasing case, and then separately there's the decreasing case, to distinguish like the green pieces of the function from the red pieces. Okay, so but you can just express both formulas simultaneously using that single formula, because you see that in the increasing case, this derivative here is positive, because phi sub n inverse is an increasing function. The derivative will be positive, and so it coincides with its own absolute value. So in that case, it's correct to write the derivative here as just the absolute value of itself, because it's a positive quantity. But in the negative case, or in the decreasing case, right, this derivative here is negative, but you have an extra minus sign. So you see the two of those put together to just give you an absolute value around that. So that's nice, because it kind of takes two separate cases and folds them together. Gives you a formula that's valid in all cases. All right, so there it is. And now what we have to ask is, does this integral here converge? Does this integral here converge? Okay, so we need some hypothesis to force that integral to converge, because in general, why would it have to? Right? It's a question. It might converge or it might not. It just depends on the nature of that random variable. In other words, it depends on the nature of this function g. If that function g is not very cooperative, it maybe it like decays to zero on both ends. That's why it gets big or gets very large, like positive or negative. But maybe it does so extremely slowly, so that the factor y dominates, and then the integral could diverge. So there's no reason to expect in general that this integral would converge. So we're going to need some hypothesis, some main assumption that's going to try to force that to converge. And the main assumption, let me call it that actually, the main assumption to try to get the convergence of that integral to come out is the assumption that the integral of phi of x f of x dx converges. Now notice that these two integrals are very different. So this is going to be our main assumption that we're going to make throughout the rest of this entire proof. So the theorem we're proving really is that if this assumption is true, if this integral here converges, then it forces this one to converge too, this one here. Which means that our new random variable is expectable, and we know its expected value. And then you see that there's more, though. Okay, there's more to it than that, because yes, we know its expected value in the sense that we have this formula for it right here. But that's not a very good formula, because this integral is very hard to calculate. See, the function g is extremely complicated. If you look at this formula here, the function little g of y is extremely complicated. So we don't want to use that formula here, this one, to compute the expected value, if we can avoid it. So there's a little bit more to it, which is also that it turns out that these two integrals are actually equal. If this one converges, which is our main assumption, then so does the other one, and in fact the two are equal. The two integrals are exactly equal. So therefore, since the expected value of phi of x hat is equal to one of those two integrals, then in fact it's going to equal the other one as well. And then the resulting conclusion is going to be that, so yeah, the theorem we're going to be proving is that if this integral converges, then the random variable phi of x hat is expectable, and its expected value is given by that very same integral. Remember, that's the theorem we want. And you see, this integral here is much more pleasant to work with, because f will be known to us already, just because it's what we use to specify the original x hat in the first place. You can't even work with x hat if you don't know something about it. And since it's a continuous random variable, the thing you know about it is generally its density, little f. And then, of course, this is going to be known as well. So yeah, this is a very nice, much nicer formula to get the expected value here, since everything is known to you in advance, and you don't need to use this function g.